Hey, this is Scott. So, this is a brief video. It's part of the series that I'm doing on Bayesian statistics and decision making. And so, I hope you join me for Bayes03, where I introduced my intent for the series. Please see that 3 minute brief video on what I intend to cover. This is the fourth video of this particular series, and we're going to talk about the frequency interpretation of probability. So this will be fairly quick. Here's what I plan to cover today. So the frequency and subjective interpretations, some relative frequency ideas, probability equation, the law of large numbers, and statistical regularity. All right, so let's jump in. So let's look at the frequency and subjective interpretations. So everything in probability is subjective, and I'm going to do a one-off, I think, at some point that just talks about that explicitly, that there is no such thing as some universal probability. It's all in our minds, and that really is the Bayesian paradigm, is that we model our uncertainty with probability. And then, here's relative frequency. Let's look at this. Relative frequency is calculated as the number of times an event occurs divided by all possible outcomes, right? It can be based on observed results in a sample or theoretical outcomes. So that, in a nutshell, if we have an experiment, let's suppose that we're just rolling a dice in an experiment. We'll look at some of the distributions there in just a second. But if I roll a dice, I'm going to get 1 out of 6. That's going to be the odds, right? So that is the probability of a 1 is going to be 1/6. Here's a very basic formula for probability: the number of favorable outcomes of what we want. Again, so if I'm talking about rolling a 1, that is the A, versus the total number of outcomes, and that can be 1, 2, 3, 4, 5, 6, 7. So the probability of a 1 is 1/6. And so it's that simple as far as a frequentist view. And of course, you can have summations of events. And so mathematically, there's really two formulas. There's summations where we have discrete events. And then there are, using calculus, there's integrals of continuous events. So just as a quick example, that might be, the probability of something being less than 70%. Those aren't discrete. We have the real line, the values. So anyway, let me move on. So this is what we call a uniform distribution. Again, that rolling that dice 1 to 6, if it's a fair die, each roll, each number has an equal probability of coming up. We're going to assume that it cannot land on its edge. So 1, 2, 3, 4, 5, 6, a little over 16%, 1/6 for each one of those outcomes. And then we can have other outcomes too, right? So if you want to play in Vegas and you want to play dice, 7 is the lucky number. 7 pays. So interestingly, 7 is the most frequent die to come up. The combinations of 1 and 6, 3 and 4, both ways. So yeah, there's that. So the probability of a 7 is 6 over 36. If we added all these bars together, they should be 36. Each die is 6. 6 times 6 for each die, it's 36. That's the total number of outcomes possible. And then there's 6 ways to roll a 7. There's I missed one just a second ago. So there's 1 and 6, 2 and 5, and 3 and 4. So and then on each die. So that's 6 different ways. Okay, so let's talk a little bit about statistical regularity. And so it's this notion In statistics and probability theory, the random events exhibit regularity when repeated often enough, or repeated enough times. And I bolded that because that is the most important thing, right? So we never know what a single event might be. We don't know if it's going to rain tomorrow or not. But if we have a 100-year history of when it's going to rain in September, we could probably do a much better job than guessing whether it's going to rain or not by itself. And so this is from the Society of Actuaries and U.S. And it is an umbrella term that covers the law of large numbers and the central limit theorems and Gardotic systems as well. So yeah, we're not going to cover the central limit theorem, but we will, or yet we are going to talk about the law of large numbers here. But again, it's things can look random, even weather patterns or weather itself. But then if you start really looking at the patterns, it tends to be some sort of underlying mechanism for a lot of things. Not everything, but yeah. And so we can model that. That's the point of statistical regularity. We can model that uncertainty. And so this is an example of statistical regularity, and this is the law of large numbers, where we have a number of coin flips. And if we flip enough coins, what's going to happen here, we have 500 here. In the beginning, if you look at the percentages, right, so the percentage of heads, the first flip is going to be 1 or 0, right? We're either going to have a heads or a tails. So the probability of heads on the first flip is going to show up. It's going to look like a 1. And then when we do it, flip again, and we get maybe a tails, then it's going to go down to 50%. And so what happens is you're going to have this pattern where it's going to go, up and down, but it's going to, what we call converge in mathematics. It's going to converge to a steady line here, and this rate will be about 50%. Over time, given enough flips. Now, the interesting thing is we sometimes can confuse that if we do 1,000,000 flips, we'll end up with 500,000 heads and 500,000 tails. No, that's not true. That's not true at all. So you can't look at the count. What you have to look at is the percentage, the relative frequency is what you need to focus on. So the other thing that I noted here is that the law of large numbers, when we're talking about this probability, it's actually called the weak law of large numbers. There is something called a strong, and if you're into mathematics, it's difference in convergence. Convergence in probability versus convergence almost surely is the difference between those two definitions. So I just made an important distinction that, again, you're not converging to equal outcomes, but you are converging to a ratio of outcomes. The other thing that's often misunderstood is the hot hand, or so that something is due. We often kind of think when we watch basketball, if a player hasn't made baskets in a while, he's due, right, or she's due to make baskets. But that really does not turn out either. Every event is well, in basketball there is some correlation, but for the most part it's the averages over time that exist. It's not necessarily something is due, or let's just go back, not basketball. Let's just say we flipped a coin, and for 20 times it came up heads in a row. The fact that we think it's due for tails, that's not true. That's not what happens. And again, it's not the counts, it's the average. It's the law of averages that count, and that's what we're trying to model here. So we'll wrap up there. Again, I like to keep these things short. So this is part of a larger series, or I should say a playlist that I have on YouTube. But this series is more on the methodology and understanding Bayesian statistics, but I also have other things in this playlist if you want to check it out. It's under my name. and there's the title for it, or anything else I can do. So again, I really appreciate any comments. Thanks.